In our final lecture of Unit 1, we will focus on marine sediments, the material that accumulates on the ocean floor and forms a long-term record of ocean, climate, and Earth system processes. Rather than treating sediments simply as particles, we will emphasize where marine sediments come from, how they are transported and deposited, and why deep ocean basins are especially important places for sediment accumulation. Marine sediments provide one of our most powerful tools for understanding Earth's past. The slow and continuous accumulation of sediment on the seafloor allows scientists to reconstruct changes in climate, ocean circulation, biological productivity, and even tectonic activity over millions of years. Marine sediments are best understood not simply as loose material on the seafloor, but as the end product of multiple Earth system processes acting together over time. At their most basic level, marine sediments consist of solid particles that have settled out of the ocean and accumulated on the sea floor. However, what makes them scientifically important is how they accumulate and what they record. Sediments accumulate incrementally, often at extremely slow rates, which means that even small changes in the environment can be preserved as distinct layers. Each layer reflects the physical, chemical, and biological conditions that existed at the time it was deposited. In this way, marine sediments function less like random debris and more like a time-ordered archive of Earth system behavior. Importantly, marine sediments are not produced by a single process. They reflect interactions between the continents, the atmosphere, the oceans, biological activity, and the solid Earth. Material eroded from land, produced by organisms, precipitated from seawater, or generated by volcanic activity can all become part of the sedimentary record. Once deposited in stable, deep ocean environments, these materials tend to remain preserved rather than reworked or destroyed. As a result, marine sediments provide a framework for reconstructing past ocean conditions, climate variability, and long-term environmental change. Before we examine specific sediment types or transport mechanism, it is important to recognize sediments as integrated records shaped by processes operating across vastly different spatial and temporal scales. As we discussed in the previous lecture, deep ocean basins are physically stable, low-energy environments. Currents are generally slow, storms do not reach the seafloor, and erosion is minimal. These conditions allow sediment to accumulate gradually and remain preserved over long periods of time. Because deep ocean basins are far from the continental margins and tectonically quiet compared to plate boundaries, they are ideal locations for the long-term storage of sedimentary records. This is why so much of what we know about Earth's past comes from deep-sea sediment cores. Marine sediments originate from several major sources. Some sediments are derived from continents, transported to the ocean by rivers, wind, or glaciers. Others are produced directly within the ocean through biological activity, such as the shells of microscopic organisms. Sediments can also form through chemical reactions in the seawater, where dissolved materials precipitate and settle to the sea floor. In addition, volcanic activity can contribute sediment in the form of ash or fragmented rock. Understanding sediment sources is the first step in understanding what information sediments can provide. Terragenous or lithogenic sediments originate from the physical and chemical weathering of rocks on land. Once produced, this material is transported to the ocean primarily by rivers, wind, and glaciers. Although these sediments ultimately accumulate on the sea floor, their properties reflect processes occurring far from the ocean itself. The composition and grain size of terragenous sediments are controlled by several factors, including the type of rock being eroded, the intensity of the weathering, and the energy of the transport mechanism. For example, rivers tend to deliver finer grained material to the ocean, while glaciers can transport much larger, poorly sorted sediments. Wind can carry extremely fine particles thousands of kilometers from their source. In the deep ocean, terragenous sediments are most abundant near continental margins, but can also be found far offshore, especially as fine clays that remain suspended in the water column for long periods of time. Because terragenous input is sensitive to climate, tectonics, and sea level, variations in these sediments provide valuable information about changes on land as well as in the ocean. Biogenous sediments are produced directly by marine organisms, primarily from the shells and skeletal material of microscopic plankton living in the surface ocean. When these organisms die, their remains sink through the water column and contribute to sediment accumulation on the sea floor. The most important biogenous sediments are composed of calcium carbonate or silica, depending on the organisms producing them. The distribution of these sediments on the seafloor is strongly influenced by water chemistry, depth, and temperature. For example, calcium carbonate shells dissolve more readily in deep, cold waters, limiting where carbonate-rich sediments can accumulate. Because biogenous sediments are linked to biological productivity in the surface ocean, changes in their abundance and composition provide insights into past ocean productivity, nutrient availability, and even climate-driven shifts in the plankton communities. In deep ocean basins far from land, biogenous sediments often dominate the sediment record, reflecting the central role of biology in shaping the deep sea environment. Chemical or authigenic sediments form directly on the seafloor through chemical reactions within seawater or sediment-poor waters. Unlike terragenous or biogenous sediments, authigenic sediments are not transported from elsewhere. They grow or precipitate right there in place. These sediments typically accumulate very slowly, often over millions of years, and include materials such as metal oxides, sulfides, and polymetallic nodules. Their formation depends on seawater chemistry, redox conditions, and extremely low sedimentation rates that allow chemical precipitation to dominate over burial by other materials. Authigenic sediments are especially common in deep ocean basins, where low input of terragenous materials allow these slow-growing deposits to persist. Because their composition reflects the chemical conditions of the deep ocean, authigenic sediments provide information about long-term changes in ocean chemistry and circulation. Sediments reach the deep ocean through a combination of slow settling and episodic transport processes. Fine particles can remain suspended in the water column for long periods and gradually settle to the sea floor, especially in low-energy environments. This process dominates sediment delivery in the open ocean far from land. In contrast, gravity-driven processes such as turbidity, currents, can rapidly transport large volumes of sediment from continental margins into deep ocean basins. These flows are triggered by events such as earthquakes, slope failure, or rapid sediment accumulation and can travel hundreds of kilometers across the sea floor. Once deposited in the deep ocean, sediments are rarely reworked. This combination of slow background accumulation and occasional rapid delivery events creates sedimentary sequences that record both gradual environmental change and sudden geological events. One of the defining characteristics of deep sea sedimentation is its extremely slow rate. In many deep ocean basins, sediments accumulate at rates of only a few millimeters per 1,000 years. This slow accumulation reflects the low supply of material and the absence of strong physical disturbance. Although these rates may seem insignificant, they allow for exceptionally detailed records of environmental change over long timescales. Even small variations in sediment composition can represent meaningful shifts in climate, ocean circulation, or biological productivity when interpreted correctly. The slow pace of sedimentation also means that deep sea sediments integrate signals over long periods, smoothing short-term variability and emphasizing long-term trends. This makes them especially valuable for studying Earth's climate history. Marine sediments function as archives because they preserve sequential layers that reflect changing environmental conditions through time. Each layer contains information about the physical, chemical, and biological processes active at the time of deposition. By analyzing properties such as grain size, mineral composition, fossil content, and chemical signatures, scientists can reconstruct past ocean temperatures, circulation patterns, productivity levels, and even atmospheric conditions. The reliability of these records depends on the relative stability of deep ocean basins and the slow, continuous nature of sediment accumulation. In this way, marine sediments provide one of the most comprehensive and continuous records of Earth system behavior available to scientists. To access the information stored in marine sediments, scientists collect samples using sediment coring techniques. These cores preserve sediment layers in their original order, allowing scientists to examine changes through time with minimal disturbance. Interpreting sediment core requires a careful analysis and an understanding of the processes that control sediment formation, transport, and preservation. Scientists must consider how different sediment sources mix, how chemical reactions alter sediments after deposition, and how biological activity may modify the record. Despite these challenges, sediment cores from deep ocean basins provide some of the most reliable long-term records of Earth's climate and ocean history. Marine sediments represent the integrated outcome of interactions among the atmosphere, continents, oceans, biosphere, and solid Earth. They record signals generated far from where they ultimately accumulate, linking processes across the entire Earth system. Because sediments accumulate slowly and continuously in deep ocean basins, they preserve information that is often lost or obscured in more dynamic environments. This makes them uniquely valuable for understanding long-term environmental change. By studying marine sediments, scientists gain insight not only into past ocean conditions, but into how Earth's systems are connected and how they respond to natural and anthropogenic forces over geologic time. Over the course of this unit, we have focused primarily on the geological foundations of oceanography. We began by identifying Earth's oceans and seas, then explored how the Earth and its oceans formed, how humans first investigated the ocean, and how we measure and interpret the shape of the seafloor. From there, we examined Earth's internal structure, plate tectonics, ocean topography, deep ocean basins, and finally, marine sediments. Together, these topics have helped us build a framework for understanding the solid Earth beneath the ocean, how it forms, how it evolves, and how it shapes the environments in which the oceans exist. We have seen that the ocean floor is not static or passive, but it's shaped by heat flow, tectonic processes, chemical exchange, and long-term sediment accumulation. With this unit complete, we now shift our focus away from the seafloor and toward the water itself. In the next unit, we will examine the physical and chemical properties of seawater and explore how water moves through the ocean system. Topics will include seawater chemistry, waves, tides, and ocean currents, processes that operate above the seafloor but are still deeply influenced by the geological framework we have just established. The geological perspective you have developed in this unit will continue to be important as we move forward.